Hello everyone, welcome to the next lecture on the probability and stat. We will see how you can transform the two-dimensional random variables. Means if you have the given random variables x and y, and if you consider u and v as another continuous differentiable function, then how you can find the PDF as well as the joint density functions of the u and v. So you can find the joint density function of the u and v by using this relation, where g is called as the joint density function of the u and v. F is called as the joint density function of the x and y, where j is called as the Jacobian, which is defined like here. You can define Jacobians either of this way, that is x in the first column, or you can also define the Jacobians like of this x with respect to u, or x with respect to v, and then y with respect to u or y with respect to v. That's all depending on you. Either you want to use this or this is called as the Jacobian. In our last class, we have seen that how you can find the transformation of the random variable in the one dimension, that is by using here. You can see the same concept for here. This is for the one variable. We can extend them to the two variables. This is for the marginal density functions. This is nothing but my Jacobians. We follow the three-step rule in this lecture. That is, if you have the given u and v transformation, first thing is that you have to find the value of the x and y from here. That is, you can solve them and find the value of x and y and find Jacobian. Once you can find the Jacobian, you can compute this value, and finally you can find the domain of the u. How you can solve them, we will see in the couple of examples. We will discuss the 5 examples of the different kinds, so it may help you. So you can see you have to find the distribution of the x and half x minus y. So I can consider this as a u. And since we need one more variable as a v, so since it is not given to you, you can consider x either as a x or as a y or as a combination of them, any one of them. Make sure that you have to take a v in such a way that whenever you want to compute the Jacobians, it will be the non-zero. So I consider u as this and v as a y here. Then our target is to find of this. But you can see what is your target in this question. That is a distribution. If I call as a g is my function, half x minus y is u. How you can find this one from, how you can find gu from this? This is nothing but my marginal density function. So it means our first target is to find the joint PDF, and then we will find the marginal. That's very simple. You can find the value of the x and y from here. You can see y is nothing but my v. You can substitute here, you can get a x. You can find the Jacobian from this. Here you can substitute the value of partial derivative of x with respect to u is 2, with respect to v is 1. This is my 0, this is my 1. So what is the answer is my 2 here. You can substitute this value in here. What is the value of the fxy is this. You can substitute the value of the x here, y here in this expression, you will get this one. Now that's the joint density function of the u and v. Now to find the domain of u and v, what you can do is you can consider this value. Since x is greater than 0, what is the meaning of the x greater than 0? It means this value is greater than 0. What is the meaning of the y is greater than 0? Means v is greater than 0 here. So you can get the two ranges are there. So therefore the PDF is u is in from the all domains and here. Now our target is to find the marginal density function of the g. So how you can find the marginal density function of the u? It is nothing but the integration over the collection of v. How you can find the range of this is, you can draw the graph. V is greater than 0 here. V is nothing but my minus of 2u this. So which is the portion as there? So this is the shaded portion inside that here. Now if you consider this as a shaded portion, now you can take the limits. 1 from this. This is from my minus of 2u to infinity, and this is from my v is my 0 here, v is my since there are two different limits, so we will try to solve as a two different cases like here. You can substitute this v limit in the first case and here, finally for this one like this one. How you can solve this first integration is, you can easily solve that like of this. Since e raised to power x is there, whenever you substitute infinity, you will get this. How you can find this domain is, in this region 1, what is the maximum value of the u? That is my infinity minus infinity, minimum value is my 0. If you look about the second reason, that is for here, what is the minimum value is my u is my 0 and maximum value of u is my infinity. Now you can solve this integration, you will get this expression. Also, if you closely look about that, both the integrations are look like similar. The only difference is the coefficient of here. So I can write in terms of the modules. Look at the second example. Again, you have to find the joint density function and then you have to check whether u and v are independent. In this example, both u and v are given to you. So what you can do is you can start from here. So if you consider here, can you find the value of the x1 and find the value of x2? So x1 is nothing but my u by v. So you can substitute here. So this will be my here. Based on this x1 and x2, you can find the Jacobians of this. So what is that? Jacobian will be nothing but half. You can substitute the value of this. You can substitute the value of the x1 here, x2 of this in this expression. You will get here. How you can find the domain of this? So it is given to you here. You can substitute the value of the x1 and x2 here. Now always remember that how you can find the domain of this. You can consider the first two. What will happen is u is greater than 0. Now you can consider the next two. What will happen is v is greater than 0. Now you can consider the last two. It will be v is less than 0. So what is that? V is greater than 0, v less than 0, u is greater than 0 is my domain. Hence the joint density function of u and v is my here. How you can check that whether they are independent? So we all knows that you have to check that marginal density function of the u, marginal density function of the v, if the product of them will be same or not. How you can find the marginal density function of u? You have to integrate over the domain v. So if this is my u, this what is the shaded region here. So what is the limit of the v is my from 0 to infinity. What is the marginal density function of v is my here. You can simply integrate them. You will get this expression. When you integrate this, you will get this expression. Check whether this equation satisfied or not. Yes. So this means they are independent. Look at the another one is again you have to find the joint density functions and check again whether they are independent or not. You have the given u and v. You can find the value of the x1 and x2 from easily. Find the Jacobian of this, that is nothing but my v. And then you can find this, substitute this value here. What is the value of the x1 is my uv. This is my x1. This is x2. This is a Jacobian are here. How you can find the domain? You can start from this one. Again you can see from here it means uv is greater than 0. From this side, what is the meaning of that? U of 1 minus v is less than 0. And from here v is my less than 1. So once v will be less than 1, what is the meaning of that? U from here you can see that v is greater than 0, v is less than 1 from here on. So therefore the joint density function is my here. Now you can find the marginal density functions. How you can draw that? How you can find the limits are there? You can simply draw the graph. U is 0, u is 1, v is 0, v is 1. So that is my shaded portion. Now you can take over the limit v, that is the vertical lines. What is that? 0. What is that? Is 1. So 0 to 1. If you take on the horizontal axis, what is that? This is 0. This is my 1 r here. Now you can integrate them over the v. 8 u is outside. So it's v raised to power 4 upon 4. So what is that? This is nothing but my 2 of u. Similarly for here. Can you check, see that whether the product of this will here? Yes. So again it is a independent. Look at one more examples are there. Now in this case you have to find the distribution of the x plus y. So I consider u as x plus y. V you can consider either as a x or y or x minus y or any of the relation such that whenever you want to compute the Jacobian it should be a non-zero. So let's see, I consider v as a x. Then you can find the value of the u, x and y from here easily. You can find the Jacobians which is given as a minus of 1. You can substitute here. X is nothing but my v. Y is nothing but my u minus v here. How you can find the domain? So since 0 is less than of here and y is greater than 0. So whenever y is greater than 0, it means u minus v is greater than 0, means u is greater than v. Whenever 0 is less than, what is the axis? My v. So this is my here. So that is my domain is u is greater than 0 and of this one. But I want to be calculate the g of u. What is that? This is nothing but my marginal density function. So I can draw the graph of this. What is the common portion is here. Now how you can find the marginal density function of Which one I want? X plus y. X plus y I consider as a u. So I want the marginal density function of the u, that is half v e raised to power of dv. So whenever we want to take the limits on the v, so we can take this vertical strip either on this side or on this side. So if the limits are same, then we can integrate it. It's a 0 to u. It's from 0 to 2. So since there are the two different limits, so what we can do is we can divide them from here. Then we call this as a region 1 and this as a region 2. So we will compute them as a two different cases. First one is when from the 0 to u, and second one is 0 to 2. So whenever this is the there, then you can substitute this value in here. You will get this expression. Whenever you want to solve this integration, you get this expression. So this is corresponding to this region. This is corresponding to this. What is the value of the u from here? This is 0. This point of intersection is my 2, 2. So this is my 2. It means this value is for my 0 to 2. And for this value is my 2 to infinity. So hence the distribution of the u is my, whenever u lies here, this is the value for the u, then this is the PDF, otherwise here is the required answer. Look at the last example are there. So in this case you have to find the joint density function of here. So we can consider this as a u, this as a v. But the first thing is we have to find the joint density function. Since they are independent, so what is the joint density function of this? This is nothing but fx1, fx2. What is that? F of x1s are given to you, you can find here. Consider u and v as of this. Find the x1 and x2, find the Jacobians and substitute the value in here, you can get this value. How you can find the domain is, since x1 is greater than 0, x2 is greater than 0. So what is the meaning of that? U plus v is greater than 0, u minus v is greater than 0. So what is the meaning of that? Also you can see whenever x1 plus x1 and x2 both are greater than 0, so the sum will also be greater than 0. So it means v is a greater than 0 is a satisfied. So you can find the limits as of here. Therefore the PDF is, this is the required answer. So since they are nothing asked about the marginal, but if they are asking about how you can find the marginal of x1 minus x2 or x1 plus x2, then you can do this, the optional. This is not asking in the question, but you can do like this way. What is the common portion is, this is the portion. Now you can find the marginal density function of the v. Firstly, collection of the u. How you can take the u is, you can take the limits on the horizontal axis. This is my minus of v to plus of v, that is the limit earlier. But if you want to take on the horizontal axis marginal density function of the u, you have to take the limits from here, from minus of u to infinity and from plus of u to infinity. Since both the limits are different, so we have to solve these two independently. So if you again closely look about that, these values are same, the only difference is the negative sign. So you can write this as of modulus. And if you remember that this is nothing but my double exponential, or called as the Laplace distribution function. So this is the way you can solve this problem of the transformation of the two-dimension problem. In our next class we will see some more examples on these two-dimensional random variables. Till then you can simply follow this link for finding the various videos. Best of luck students. Happy learning.